Breaking the limit, what new does Starship Flight 4 bring compared to Flight 3? Welcome to the Elon Musk Signal channel. Starship is gearing up for its fourth test flight. Valuable lessons learned from Flight 3 will be applied to optimize Flight 4. So what will Flight 4 focus on improving and fine-tuning? Let's explore the fresh developments between Flight 3 and Flight 4 together. This video will also touch on expectations and predictions for this exciting Starship program. Let's dive right in. According to recent updates, Starship Flight 4 will heavily concentrate on perfecting its critical defense system, the heat shield. In Flight 3, the primary goal was to achieve Starship's atmospheric re-entry point. Now that this milestone has been reached, SpaceX needs to ensure that Starship can survive through that rigorous process. Prior to Flight 3, investing hundreds or thousands of hours into perfecting the heat shield was unnecessary if Starship couldn't reach the re-entry point. But now, everything has changed. On the S-29 version designated for Flight 4, SpaceX engineers have worked to eliminate cross-joins on the heat shield, including one join at the liquid oxygen (LOX) tank in the middle of the spacecraft. Additionally, they have removed some panels on the nose cone and roughened the metal surface underneath to enhance the adhesion for the new heat shield tiles. With meticulously improved heat shields, there is hope that Starship can withstand the tremendous heat during its return journey to Earth. However, if Starship fails to maintain proper orientation before re-entry, even the best heat shield cannot protect it. Flight 4 is not only a test of the booster's re-entry capability, but also an opportunity for Starship to shine. Compared to the 3 previous test flights, Starship on Flight 4 is expected to surpass the challenging re-entry phase thanks to the upgraded heat shield. Starship's Flight 3 encountered issues in maintaining orientation during spaceflight. The cause was identified as blockages in some roll control valves. To address this issue, SpaceX has upgraded the hardware to better withstand similar blockage incidents. They have also added a backup roll control system, enhancing operational safety for Starship. Not only Starship received upgrades, its sibling, the Super Rocket Pusher Booster, also got its share of enhancements. Booster 11 seems to have undergone significant improvements, primarily focusing on structural reinforcement. A notable point is the methane tank of Booster 11, which has been substantially reinforced, with the number of internal stiffeners increased from 24 to 74, tripling compared to Booster 10. Additionally, SpaceX engineers have added additional reinforcement panels at the head and tail of the LOX. Not stopping there, the lower foot of Booster 11's pedestal has also been reinforced with additional struts and reinforcement, nearly doubling the thickness compared to the previous version. These improvements aim to increase the structural rigidity of Booster 11 when unfueled, while also mitigating strong oscillations during atmospheric re-entry, a factor that will be discussed further in the next section. Finally, the protective shield for the vent holes on the LOX tank has also been significantly reinforced, promising to improve durability in harsh environments. SpaceX has also made some minor changes to the control system of Booster 11 to enhance accuracy and responsiveness. They continuously monitor and analyze data from test flights to further improve Booster and Starship. With these comprehensive upgrades, Booster 11 promises to play a crucial role in propelling Starship into orbit and achieving SpaceX's space conquest goals. Flight 4 is a significant milestone for SpaceX to achieve the goal of reusing Starship and Booster multiple times in the future. Although Starship has made significant strides in Flight 3, SpaceX still needs to accomplish key objectives in Flight 4 to get closer to the goal of reusing the Starship rocket. One of the biggest challenges is successful landings for both Starship and Booster. Unlike conventional rockets, SpaceX is testing the skip method of bypassing the re-entry burn phase for Booster. Instead, they hope the stainless steel skin of the booster can withstand the tremendous heat when penetrating Earth's atmosphere, similar to how Rocket Lab's Electron rocket operates. Flight 3 demonstrated the survival capability of the booster during re-entry. However, it lost control at lower atmospheric levels. This is the main reason Booster 11 underwent significant reinforcement in Flight 4. Therefore, whether Booster 11 achieves the soft water landing goal will be a notable highlight of Flight 4. Accordingly, the booster will be precisely directed to a specific point in the Gulf of Mexico to test its responsiveness before moving on to the more ambitious goal of utilizing the rocket catcher, Mechazilla, on the launch pad. Moreover, the flight control software has also been significantly improved to ensure that Starship can perform complex maneuvers during ascent, reach the desired altitude, and then re-enter the atmosphere safely. This was something Starship failed to do in Flight 3. If all goes smoothly, we will witness the effective operation of Starship's control fins, aiding stable flight during re-entry. If Flight 4 is successful, Booster 11 may achieve the soft water landing goal, paving the way for rocket-catching efforts in Flight 5. However, SpaceX might conduct several precise ocean landings to ensure safety before embarking on the ambitious catching maneuver. But the most interesting aspect of Flight 4 perhaps lies in the landing phase. If Starship overcomes the re-entry challenge, it will perform a bold flip maneuver and land using propulsive landing instead of the belly flop style used in the previous 3 flights. Many wonder why SpaceX didn't implement the belly flop and propulsive landing from the start. It's possible SpaceX wasn't sure if Starship could fly that far, and adding complex control software for the belly flop maneuver wasn't necessary. Additionally, the current Starship can only perform one engine relight. Furthermore, Flight 4 marks the first time SpaceX removes the hot staging ring immediately after the boost backburn phase ends. This helps reduce the weight of the booster, improving efficiency for the landing burn. Although the exact reason hasn't been disclosed, it's certainly an intriguing detail to follow during the mission. However, Flight 4 may not include the simulation of Starship's deorbit burn. Instead, SpaceX prioritizes demonstrating safe re-entry rather than the ability to reignite Raptor engines in orbit. Simulating the deorbit burn is crucial to ensure that Starship can safely descend to Earth, avoiding becoming a 100-ton unguided brick in space. SpaceX may conduct this test in future test launches. Flight 4 promises to bring spectacular images of Starship's re-entry and landing process. This is a significant step towards Starship's goal of safely ascending to space and returning to Earth for reuse, paving the way for a new era of space exploration. The success of Flight 4 will be a solid stepping stone for SpaceX to pursue more ambitious goals. If SpaceX can complete the test of reigniting Raptor engines in orbit by the end of this year, they may deploy the first batches into space, including Starlink satellites, using Starship as the launch vehicle. We've just explored the technical challenges that Starship and Booster must face in Flight 4, significant improvements applied to enhance performance, and hopes for magnificent successes in the future. Thank you for watching the entire video. Leave your comments on today's broadcast. Don't forget to like, share the video, and subscribe to the channel to stay updated on interesting information about technology and the journey of space exploration. Goodbye, and see you in the next video.